Hello and welcome to the next session of our sustainability series. My name is Ricardo Pimentel. I'm a technical director for buildings here at Pell Frischmann. In today's session, we are going to look at how structural engineers can promote a circular economy in the built environment. Waste has the potential to become valuable low-carbon materials. Since the resources and energy required to manufacture the materials are avoided, reclaimed components are a powerful solution to tackle the climate crisis. There is a growing interest in the industry to use reclaimed components, mainly by structural engineers, as most of the embodied carbon of a building relates to its structure. Pre-demolition audits facilitate the journey from waste to reclaimed materials capable of being reused. The flowchart explains what the pre-demolition audit entails. A building is flagged for demolition. The audit process assesses the quantities and condition of existing materials on site and proposes recommendations for their recovery. We include advice from our network of industry specialists, ensuring that our recommendations enable the reuse potential of each product tailored for its specific project. The findings of the audit help our clients achieve planning and are important to deliver sound circular economy statements, as well as produce demolition specifications. There are many ways to enable a circular economy model. A building can be retained, retrofitted, or reused, whilst a component can be recovered to be reused or recycled. Preserving and extending the life cycle of current assets, as well as enabling future recovery of construction components, are key to enable a circular economy model in the built environment. As structural engineers, the principles to enable a circular economy model can also relate to material choice, and why not specify reclaimed components, if possible, and design for deconstruction and reuse to enable end-of-life recovery of valuable components. Some materials offer greater opportunities to be reclaimed and reused. For example, steel has higher recovery and recycling rates because the material can be easily sorted, is robust, and remains a valuable component with its original mechanical properties through multiple life cycles. For other materials, such as concrete or timber, although recovery and recycle are possible, such scenarios are less likely to occur. The components are likely to be downcycled, losing most of their value. We should keep in mind that our main goal should be to reduce emissions now. Delivering carbon-intensive solutions to make them demountable is not the way forward, as well as focusing on one specific material. History tells us that combining different materials is the way forward to achieve efficient solutions. Nowadays, structural efficiency alone is not enough, and the environmental impacts of our choices and advice should play an essential role in decision making. Steel is unique and deserves special attention as it is 100% recycled. Modern steel manufacturing techniques can use up to 100% recycled content, closing the loop. If steel components are not reused, they will be recovered and recycled to produce new components needed in the construction or other sectors. A simple embodied carbon assessment may not be able to capture the big picture of what really happens in our industry and how our different design options affect the built environment. The end-of-life benefits of steel shall not be neglected. Reuse of components is the best option to tackle the climate crisis and reduce emissions. Steel is clearly the best material to enable such practice, but is steel reuse practice feasible? Recent developments and guidance make it a reality. The new generation of design standards, to be published in the short term, is likely to be more transparent in accepting the use of reclaimed components, while its guidance on the matter is nowadays readily available. Existing practical examples of steel reuse cover small-scale projects, to office buildings and even the London Olympic Stadium, completed at a time when guidance was very limited. Steel is prefabricated, enables off-site manufacture and can be demountable. However, float plates can hinder reusability. Permanent connection between building layers shall be avoided to facilitate the recovery of components and enable circular economy. One example is given of a dry floor plate using timber and finishes over steel beams. Floor cassettes can also be considered to improve prefabrication and recovery. Another example is the use of demountable shear connectors for composite beams. Connecting steel and concrete is typically required for robustness to increase structural efficiency and consequently reduce the steel tonnage and carbon footprint of a floor. To promote the circular economy, the typically welded studs can be replaced by structural bolts. Guidance on this system is also likely to be included in a new generation of design standards, which is indeed promising. A qualitative summary of how we can adapt our practice and decision-making is shown. It also illustrates how we can advise our clients. Performance, robustness, and costs are typically considered while comparing different solutions, but aren't other indicators such as carbon footprint and circular economy potential equally important? A holistic view of each solution is needed to promote a step change in our industry and practice. Tools such as our in-house developed embodied carbon infrastructure help with this exercise. The message is wishing to specify reclaimed components alone is not enough. We, as structural engineers, have the responsibility to enable their recovery through pre-demolition audits, but also to deliver clever and sustainable structural solutions capable of retaining the value of construction components in the market for as long as possible. Thank you for listening.